Hello everyone, I'm Vamsi Pulusu, a technical architect and lead data engineer at Ford with over 16 years of experience. My research paper is titled Demystifying Modern Data Pipeline Architecture from Traditional ETL to Cloud Native Streaming. Think back to a time when you had to wait all night for a critical business report to process. That was traditional world of ETL. But today, the digital factory never sleeps and our data can't either. Over my career, I've been on the front line of this dramatic evolution, and today I'll share how we are moving from batch-oriented mindset to the world of cloud-native streaming and what that means for how we turn data into value. Here is a look at what we'll cover today. We'll start with evolution of data pipeline architectures, discussing the limitations of legacy systems. Then we'll dive into modern architectural patterns that emerged. We'll look at the tool evolution landscape, examine critical design consideration for building resilient pipelines, and finally look at emerging trends and practical migration strategies for organization. The key takeaway of modern data engineering revolution is the shift from batch to real-time processing. Traditional approach relied on scheduled batch processing using centralized systems. Now, modern reality involves distributed real-time and cloud-native architectures. Two main factors drive this. The business driver has an intense need for immediate insight and operational intelligence. The technical driver is the demand for greater scalability, better cost, efficiency, and overall flexibility in our data systems. Traditional ETL limitations. Why change was inevitable? The traditional ETL framework faced significant constraints. First, batch processing in Windows typically occurred overnight to avoid disruption operating systems, which severely limited data availability when businesses started demanding real-time analytics. Second, the centralized design meant single point of failure with limited recovery options that often required completely reprocessing the data. Third, rigid infrastructure meant performance improvements depending on expensive hardware upgrades involving high upfront cost and complex capacity planning. Fourth, traditional systems were built primarily for structured data and struggled to handle the explosion of semi-structured logs and streaming data for new sources like devices and web applications. Finally, they also suffer from vendor lock-in due to proprietary query extensions. The cloud storage revolution, decoupling storage from compute. The introduction of cloud storage, specifically object storage like S3, Azure Blob Storage, or Google Cloud Storage, was fundamental to enabling modern data architecture. The most profound change was the decoupling of mechanisms between storage and computing. Before the cloud revolutions, storage and computing were tightly bundled in expensive fixed capacity warehouses. If you needed more processing power, you usually had to buy more storage and vice versa. After the shift, we gained access to practically unlimited, extremely cost effective object storage, which can scale independently of our processing clusters. This architecture freedom delivers several key benefits. First, the pay as you go principal model shifts infrastructure costs from large capital expenditures to variable operation costs, making data scale accessible to every organization. Second, it enables schema or read flexibility. We can now store raw data in its native format, applying transformation later, preserving data integrity rather than forcing it into rigid predefined structure upfront. Finally, cloud storage offers native redundancy, durability, and it inherently supports all formats, structured, semi-structured, unstructured, which was impossible with traditional databases. Modern architectural patterns overviews. As data systems mature to handle modern challenges, several key architectural patterns emerge. These patterns represent different philosophies for how we structure and process data on a scale. We'll explore the five most influential. First, the Medallion architecture. The pattern defines transparent quality layers, bronze, silver, and gold, for data refinement, ensuring governance, and quality are built into the pipeline. The Lambda architecture. This is a dual path approach using a batch layer for complete historical accuracy and speed layer for real time insights. The Kappa architecture. Application of Lambda. This pattern adopts a stream first model using a single processing engine and an event log as a source of truth for both real time and historical views. The Lakehouse Paradigm. This unified approach brings the transactional feature and performance of data warehouse directly onto the low-cost storage of data lake. And finally, data mesh. This is a less technical architecture and more organizational structure, decentralizing data ownership and treating data as product owned by domain teams. Now, I would like to discuss about the Medallion architecture. The Medallion architecture, model after Olympic medals, organizes data refinement into discrete quality levels. The bronze layer is where raw data lands into lands without modification, ensuring complete source fidelity. Its validation focuses usually on completeness. The silver layer is a trustworthy foundation. Here, raw data is transformed by standardizing format, fixing inconsistencies, and applying quality and governance rules. The gold layer is a data shape for business consumption. It includes purpose-built structures like star schemas and pre-aggregated metrics. The main benefit is that it creates clear quality boundaries and ensures reproductive processing. This makes it ideal for organizations with strong governance requirements. Now, I would like to discuss about the comparison between the Lambda and the Kappa architecture. Lambda and Kappa architecture represent different philosophies for handling both historical and real-time data. The Lambda architecture uses parallel batch and stream processing paths. The batch path handles comprehensive historical analysis, while the speed path provides immediate, if preliminary, insights. Its main downsides are higher complexity and the necessity of dual code-based maintenance for transforming logic. Architecture simplifies this by adopting a stream processing first approach. It uses a single append only event loss as the definitive system of record. Batch processing is conceptualized as just streaming with an unlimited time window. This results in simpler maintenance and unified processing model. Now I would like to discuss about the Lakehouse. The Lakehouse paradigm represents a powerful convergence. It addresses the historical fragmentation of having separate data lakes for raw storage and warehouse for structured analytics. It combines lake flexibility, low-cost storage with data warehouse performance. Key features include implementing warehouse capabilities like asset transactions and schema enforcement directly onto cloud storage objects. It supports multi-workload support for BI, ML, and streaming and provides unified governance. The business impact is the elimination of data duplication, fragmented governance, and integration headaches. Now I would like to discuss about the data mesh domain-oriented approach. The data mesh pattern is less about technology, more about organization shift. Its core principle is to treat data as a product owned by domain team. This is designed to solve the scaling bottlenecks present with centralized data teams. Key domain-oriented ownership, a self-serve data platform, federated governance, and data products with clear interfaces and quality assurances. The primary benefit is organization scalability and better alignment with specific business domain. The primary challenge, however, is that requires significant organization change. It's a socio-technical transformation. I would like to discuss about the tool evolution timeline. Let's look at the tool evolution timeline. We can segment this journey into four areas. In 90s and 2000, the focus was traditional ETL tools like IBM DataStage and Informatica, visual interfaces, and monolithic batch-oriented design characteristics. From 2010 to 2015, distributed processing frameworks like Hadoop and in horizontal scaling and code-first approach. Between 2015 and 2013, we saw the rise of open source orchestration tools like Airflow and Perfect. Alongside early cloud services, these enabled decoupled processing and serverless executions. From 2020 onwards, the landscape was stream first, unified processing, and ML integration. We now see real-time capabilities, declarative interfaces, and specialized systems for machine learning. Modern tool categories. The current landscape has four main categories of tools. Orchestration framework like Apache Airflow and Prefect focus on scheduling dependencies and monitoring decoupled from actual data processing. Cloud native services such as AWS Glue and Azure Data Factory offer serverless execution and consumption-based pricing, fitting well with variable workloads. Streaming platforms like Apache Kafka and Spark Streaming are essential for low latency real-time insight. And finally, processing engines like Apache Spark, Flink provide the power of complex distributed computation. Your selection criteria for choosing a tool must extend beyond features to include team skills, operational requirements, cost model, and integration needs. Critical design consideration. Moving to modern distributed system introduces a new set of challenges and operational necessity. We must address five critical design areas: data governance and lineage, tracking data provenance across complex environments, quality validations, shifting from periodic checks to continuous assurance, and performance optimization, leveraging distributed techniques like partitioning, security and compliance, implementing data-centric protection and access controls, integration challenges, managing the coexistence of real-time and batch workloads, and distributed systems. In distributed hybrid and multi-cloud environments, maintaining visibility is a significant challenge. Governance has evolved from compliance checkbox to an operational necessity. Our solution must include automated lineage tracking at multiple levels from dataset to column and even record level for provenance. For environments with incomplete instrumentation, emerging techniques include stick lineage, which uses statistical methods to infer transformation relationships. The business value is clear: rapid impact analysis during failures, simplified troubleshooting of inconsistencies, and necessity audit trails for compliance. Quality validation framework. Data quality assurance must now be continuous and automated now, not just periodic and manual. Modern frameworks implement multi-dimensional validation, syntactical correctness, semantic validity, contextual appro- appropriateness. The implementation architecture has evolved to distributed components that execute checks at each transformation boundary in streaming, and this is achieved through specialized stateful operations that implement validation logic directly within the execution model, detecting anomalous patterns in continuous data flows. Emerging trends: serverless data processing. Looking forward, serverless data processing represents a profound paradigm shift. Key characteristics include elimination of explicit infrastructure provisioning, dynamic resource allocation, and a shift to consumption-based pricing. This has a significant design impact, encouraging architectures composed of smaller focused processing units with clear boundaries rather than monolithic transformation jobs. The benefits are powerful: automatic scaling, significant cost optimization, and operational simplicity. AI ML integration data pipelines meet machine learning. The integration of AI and ML has driven specialized artificial innovation. Feature stores have emerged as a critical component. These are specialized systems that manage life cycle of machine learning features, providing versioning, access control, and ensuring consistency between training and serving. Modern service pipelines integrate real-time inference delivery into core data pipelines. A key requirement is point-in-time feature accuracy for valid model training and lineage tracking for modern. The business impact is faster model deployment, consistent feature engineering, and unified infrastructure supporting both traditional BI and advanced ML workloads. Data contracts and schema management, formal agreement for data exchange. A data ecosystem, decentralized data contracts and formalized schema management are critical for maintaining stability. The purpose of these contracts is to establish explicit agreements between data producers and consumers. Components specify data structure, quality characteristics, and delivery patterns. The main benefit is enhanced stability in distributed systems by setting clear expectations. This implemented via version schema registries and with sophisticated compatibility checking that validates proposed change against historical usage to prevent breaking downstream consumers. Migration strategies, practical approaches to modernization, table of approach, risk timeline, and key factors. Finally, migrating from legacy architecture is a significant undertaking, and a wholesale replacement is rarely feasible. We must adopt in incremental strategies. The table outlines a few proven approaches. Pattern-based modernization identifies more common processing patterns in systems and creates standardized reusable modernization approach for each. Hybrid execution uses gateway component to maintain consistent interface while underlying implementation transition gradually. Specialized connectors allows modern processing framework to efficiently integrate with existing data sources through adapter, pattern, and format bridges. And domain by domain starts with non-critical businesses domain and expand progressively. This low risk phase approaches minimize business disruptions, sorry, and allows organizations to demonstrate value incrementally. Key takeaways, essential insights for data leaders. To summarize our journey, here are the essential insights for data leaders. There is no single architecture. The future lies in thoughtfully composed system that aligns with specific business contexts. Adopt incremental migration to modernize and minimize risk gradually. Governance is critical. Lineage tracking and quality management are operational necessities in distributed environments. Real time is standard. Streaming capabilities are becoming basic for business responsive. Finally, remember that organization change is essential as a technology. Recommendations action items for organizations. For those looking to embark on this modernization journey, I offer these practical action items. Assess current state, inventory your existing architecture, and identify the key pain points. Define target state. Use architectural patterns like Medallion or Lakehouse that align with your strategy business needs. Start small. Begin your migration with non-critical domains or workloads to build expertise. Invest in governance. Implement lineage tracking and quality framework early in the process. Build skills. Develop the necessary cloud native and streaming processing capabilities within your teams. And with this, I conclude. Thank you. This transformation is ongoing, and by embracing cloud native principles and thoughtful design, organizations can build the resilient, adaptable data pipeline necessary for future of operational intelligence. I conclude, and thank you for giving me this opportunity. Thank you.